So in this class, we will discuss about the strain displacement relations. In any problem of elasticity, so whenever a body is subjected to some external loading like this, you know that stresses will develop within the body based on the nature of the force acting on the body. So those stresses will be developed due to the strains induced within the body. So actually strains can be measured, but stresses only can be calculated by knowing the stress strain relationships. So the strain is nothing but an idea about how much the body deforms. So you will be having three directions, x, y, z directions in general. So whenever some load is applied at some point, let us say here P is the point. At this point we will have some displacement. It may shift to some other point due to the application of the external forces. So this is the displacement. This is known as the displacement. The displacement can be measured in all the three directions, x, y, z directions. So I am going to take those displacements as u, v, w. So u, v, w, they are displacements along x, y, z directions of that particular point. These displacements will be coefficients of x, y, z. So that means in a three-dimensional stress system, displacements u, v, w, they are all functions of x, y, z. So they depend on from point to point, they change, the displacements will change. And of course, the net displacement, what you are going to calculate, S is given by square root of u square plus v square plus w square in the vector form. So all this you might have learned. But anyway, sometimes in an elasticity problem, they may give the displacements as functions of x, y, z. u, v, z, u, v, w, they will be given as functions of x, y, z. And they were asked you to find out the strain components. So for that we require the strain displacement relations. So in this class we will see what are the strain displacement relations in a 3D stress system. So there will be 6 strains in total, components in total at a particular point in a 3-dimensional stress system. Epsilon x, epsilon y, epsilon z, they are called as the normal strains. So normal strains because they will be acting perpendicular to the cross-sectional area along x, y, z directions. Similarly, you have shear strains. 3 components of shear strains: gamma xy, gamma yz, and gamma z, the zx. They are the shear strains in xy, yz, and zx planes. So understand that I have written a sketch here. I will take a 3-dimensional element like this. And let me choose x direction like this, y direction like this, z direction like this. Now the respective displacements along those 3 directions are u, v, w. In x direction it is u, in y direction it is v, in z direction it is w. So I have shown here the directions of epsilon x, epsilon y, and epsilon z. Epsilon x will be is the normal strain in the x direction. Epsilon y is the normal strain in the y direction. Epsilon z is the normal strain in the z direction. Similarly, here I will take 3 planes here. So one plane is xy plane, second one is yz plane, third one is zx plane. So xy plane is here. So xy plane actually you can see here if you take x, the x direction, the x is like this, x is measured like this, y is measured like this. So these 2 dimensions will constitute the xy plane. That means in this diagram, the front face and the back face, they are the xy planes. Then coming to yz plane, y is measured like this, z is measured like this. That means the left face and right face, they form the yz plane, and zx plane is nothing but the top and bottom planes. So like this, in a 3-dimensional element, you will be having 6 planes, out of which 2 will be xy planes, 2 will be yz planes, 2 will be zx planes. So these shear strains will be acting in these planes. Okay. So all this I have explained in the first video. Please refer to the first video, stress at a point. So in that I have explained neatly about the 6 stress components as well as the strain components, how they act, those directions, everything. So once you are given these x, y, this u, v, w as functions of x, y, z, we can always find out the strain components, 3 normal strain components, these 3 and 3 shear strain components using a partial derivative formula. Actually, we can derive all this. So here the normal strain components are given by, so you know that strain is nothing but change in the dimension divided by original dimension. In SY we have studied about that. So that means generally we can write epsilon as delta L by L. So this is the basic definition of strain in SY, strength of materials. So here this delta L I am going to take it as dou U. So dou U is the change in dimension in x direction divided by L is nothing but dou x. So that means delta x. Actually this delta x that can be written in the partial derivative form like this. So this gives the strain in x direction. Very simple. So delta L is nothing but dou U in x direction and L is nothing but dou x. Similarly in y direction, so it will be dou V by dou y, and in z direction it is dou W by dou z. So these are the what we can say normal strain components along the 3 x, y, z directions. And coming to the shear strain components, gamma x, y, gamma y, z and gamma z x. So shear strain is nothing but the angles. So they are the angles made due to the deformations. Angular deformations are nothing but your shear strains. Linear deformations are nothing but your normal strains. So gamma xy is written like this. So how to write this? Already I have explained in the earlier videos, you can refer. So if you want gamma xy, which is nothing but the shear strain in xy plane, how to write that is? So this x and y will come in the denominator, dou x, dou y. So like this it will come. And in the numerator, the other displacement component will be there. For example, the displacement component in y direction will come here, that is v. Displacement component in x direction will come here, that is u. So this is how we have to write. It will be interchanged. Similarly for gamma yz, so yz is written here, wv will be written here. Zx, gamma zx, zx will be written here, u and v will be written here. So this is how we can write the 6 strain components at a point when a material is subjected to some external force. Now I will take up a problem wherein you are asked to find the strain components given the displacements. So here the displacement components are given like this. They are all functions of x, y, z. U is equal to 0.01 y square z, 0.1 y square z plus 0.25 x, y, z. So you can see that they are functions of x, y, z. So v is equal to, you have 0.03 x square y, 0.03 x square y plus 0.04 x square yz. So this is v. Then w is given by 0.25 xyz, 0.25 xyz minus 0.05 xyz square. So these are the 3 displacement components in x1, xyz directions in terms of xyz. The question is, determine the strain tensor. Determine the strain tensor. Strain tensor. So strain tensor is denoted by epsilon ij like this. At the point, so he has given the point -1, -2, 3. At the point -1, -2, 3. So it means at x is equal to -1, y is equal to -2, z is equal to 3. What is the strain tensor we have to find out? So the solution goes like this. So since he has given u, v, w as functions of x, y, z, if you differentiate them partially with respect to x, y, z, you can get the strain components. Let us see one by one. U is given like this. What I do here is, first I will write all the 3 derivatives. So I will differentiate u partially with respect to x, then with respect to y, then with respect to z. So when you are differentiating partially with respect to x, y and z are treated as constants and y and like that similarly. So dou u by dou x now. So this becomes a constant, only this term will be there, 0.25 yz, because y and z they are treated as constants, the derivative of x is 1. So now we need this value at this point. Please note that at the point x is equal to -1, y is equal to -2, z is equal to 3, we need the values of the strain components. So let me substitute that. So 0.25 into -2 into 3. So later on we will simplify. So this is about dou u by dou x. Then I will take dou u by dou y. So differentiate the u with respect to y partially. When you are differentiating with respect to y partially, x and z they are constants. So here this becomes 2y. So 2 times this is 0.02 yz. So that is the differentiation of this. Next here plus 0.25 xz. Xz will be. So if you simplify this, if you substitute for x, y, z, you get 0.02 into y is -2, z is 3 plus 0.25 into x is -1, z is 3. So this is about dou u by dou y. Next dou u by dou z. I will write with respect to z we have to differentiate now. Treat x and y as constants. So 0.01 y square will be there first term plus 0.25 xy will be there. Now substitute once again here. 0.01 y square is -2 square plus 0.25 into x is -1, y is -2. So we have to simplify this also. So these three are the values of the derivatives. Now let me write the values now. The first value is 0.25, that is negative 0.25 into 6. It becomes 1-1.5. The first value is -1.5. Second value I will take that is minus 0.02 into 6. Then minus 3 into 0.25, that is 0.75. So it becomes minus 0.87. Minus 0.87. Now the third value is 4 into 0.04, that is 0.01, that is 0.04. Then plus 0.25 into 2 is 0.5. So it becomes 0.54 positive. So these three are the values. Next, I will take the second function, that is v I will take. Once again I will partially differentiate v with respect to x, v with respect to y and v with respect to w. So these three we will calculate now. So when you are differentiating this v with respect to x, y and z are constants. So this becomes 2x, that is 0.06 xy. And this also becomes 2x. So since it is 2x, it is 0.08 x, y, z. Now let us substitute the values of x, y, z here. 0.06 into x is -1 into y is -2. Then plus 0.08 into xyz, that is -1 into -2 into 3. So we have to simplify this. Next, dou v by dou y. With respect to y, we have to differentiate 0.03 x square plus 0.04 x square z. Substitute for x and z here. 0.03 into -1 square plus 0.04 into -1 square into 3. So that is what we get is equal to, we will simplify that. Dou v by dou w is 0.2, dou v by dou z is 0.25 xy minus here 2 2z will be there, that is minus 0.1 you will get x, y, z. So substitute the values 0.25 into minus 1 into minus 2 minus 0.1 into minus 1 into minus 2 into 3. So once again let us simplify this. The first value will be 0.06 into 2. Second will be plus 0.08 into 6. So the value is 0.6 positive. 0.6. Then you have dou v by dou y, 1 into 0.03, that is 0.03 plus 0.12. So it becomes 0.15. So please calculate correctly and write. So third value will be this is 0.25 into 2, that is 0.5, and this becomes 6. 6 into 0.1 means it is 0.6 with a negative sign, minus 0.6. 0.5 minus 0.6, which becomes minus 0.1. So this is the second set of value. Now the third set is we have to take this w now and differentiate with respect to x. Dou w by dou x, dou w by dou y, dou w by dou z. So these three values we find out now. Dou w by dou x, differentiate with respect to x, taking y z constants. So dou w for this. So here I have to treat y and z as constants, so it becomes 0.25. 0.25. The second value will be 0.25 yz. 0.25 yz. And this term will be minus, so we have to differentiate with respect to x, minus 0.05 yz square. So which becomes 0.25 into minus 2 into 3 after substituting for y and z, minus 0.05 into minus 2 into 3 square. This is one value. Dou w by dou y is 0.25 xz minus 0.05 xz square. That is 0.25 into minus 1 into 3 minus 0.05 into minus 1 to minus 1 into 3 square. And the third value dou w by dou z is 0.25 xy minus this I have to take it as 2z sorry, here I think I have dou v by dou z here 0.25. This is wrong. So I should be very careful here. Let me, dou v by dou z is this first term will not be there. Here it will be 0.04 x square 0.04 minus 1 square into minus 2, which is 0.04 into 0.04, this is negative, it becomes negative, minus 0.08. Yes, so you should be careful. Huh? So now here dou w by dou z, so first term is this, minus second term will be, with respect to z means it is, it becomes 0.1 minus 0.1 times x y z. Okay. So now 0.25 into minus 1 into minus 2 minus 0.1 time into minus 1 into minus 2 into 3. So this is the value. Now let us calculate that and write. First value here is minus 6 into 0.25, which is minus 1.5. This value is 9 into 5, 9 into 2, 18. So this becomes plus, minus to minus plus, 18 into 0.05. So it becomes minus 0.6. Next, second value is minus 3 into 0.75, that is minus 0.75, minus 3 into 0.25, minus 0.75. This value is positive, plus 0.05 into 9 will be 0.45. So it comes out to be minus 0.3. Next, lastly, we have 2 into 0.25 is 0.5, and this is minus 0.6, which is minus 0.1. So these are the values of the derivatives at that particular point. Now let us write the strain components. Now epsilon x is nothing but dou u by dou x. Now let us write down the strain components. 3 normal strain components will be there, 3 shear strain components will be there. So normal strain components are epsilon x, which is dou u by dou x. Directly you can give the value minus 1.5. So strain has no unit. So this is at the point minus 1, minus 2, 3. So it varies from point to point because the values of x, y, z vary. Dou u by dou y is epsilon y. Sorry, dou v by dou y is epsilon y. Dou v by dou y you are going to get here, it is 0.15. And then epsilon z is dou w by dou z, which is the last value, which is minus 0.1. So these three are the normal strain components. Next, shear strain components are gamma xy. Gamma xy, according to that, it is dou v by dou x, dou v by dou x plus dou u by dou y. So dou v by dou x is this value 0.6 plus dou u by dou y is minus 0.87. So I think you get minus 0.27. Next, gamma yz. Gamma yz is dou w by dou y plus dou v by dou z. So dou w by dou y is minus 0.3, dou v by dou z is minus 0.08, which is minus 0.38. Next, lastly, gamma zx, which is dou u by dou z plus dou w by dou x. Dou u by dou z is 0.54, dou w by dou x is minus 0.6, so you will be getting minus 0.06 is the answer. So these are the strain components you are going to get. So now let me write this in tensor form. So since you have asked the strain tensor, so obtain the strain tensor is asked. So strain tensor is given by epsilon ij. So this is how strain tensor is denoted. It is given by epsilon x, epsilon y, epsilon z will come in the principal diagonal elements. Then the remaining is symmetric. So gamma xy by 2 will be there here. Gamma fz by 2 will be there. It is symmetric. Therefore, this becomes gamma xy by 2, gamma xz by 2, and this will be gamma yz by 2. This is gamma yz by 2. Now, we know all the values. Now we can write the normal strain values will become the principal diagonal elements. Minus 1.5, 0.15, then minus 0.1, and gamma xy. So gamma xy is minus 0.27. Divided by 2 means it is minus 0.135. So this also becomes minus 0.135. Symmetric, the symmetric tensor. Next, you have gamma zx, which is minus 0.06 divided by 2 means minus 0.03. This will be minus 0.03. Then gamma yz minus 0.38 divided by 2 means minus 0.19, minus 0.19. So this is the strain tensor at the point minus 1, minus 2, 3. So this completes the problem. That means always in any analysis problem, whenever an external force acts on a body, in elasticity we consider a point. So in strength of materials, of course, we deal with average stress value, whereas here we are going to take the stress at a point. That is the meaning. So whenever an external force acts on a body, displacements will occur at all the points, and due to those displacements, strains will be developed and stresses will be developed. So UVW, they are the displacements in the 3 directions, XYZ directions. Correspondingly, you will be having 3 normal strains and 3 shear strains, and you can find out the strain components by knowing the displacement components using these strain displacement relations. So these 6 relations, they are called as the strain displacement relations. 3 normal strain components, 3 shear strain components, and displacements are functions of XYZ. They depend on the coordinates of the point. So therefore, at each and every point, the strain values will be different, stresses value will be different. So that is why we can say that elasticity is an advanced over the strength of materials. In strength of materials, we deal with only average values, whereas of course maximum values we find at some critical sections only, whereas in elasticity we can find out the stresses and strains at all the points when a body is stressed.